So what is the main reason as to why the sky is blue? Okay, number one, guys, the sun. If you're looking at the sun directly from space, through the vacuum of space, it's not going to look yellow. All right, because it's the source of our colors, right? Because it is the source of our colors, it's going to look white. All right, so why is it that we end up seeing it as yellow? The reason why we end up seeing it as yellow is because the color blue gets subtracted from it. And the color blue gets subtracted from it because of scattering. So the blue light is going to get scattered more than any other color. We just got scattering, that's the absorption or emission of light. And the atmosphere is 78% nitrogen. So evidently, most of the molecules making up the atmosphere have a tendency to absorb and emit blue more than any other color. All right, that's the modern way of looking at it. The classical way of looking at it.
If the sun gives off white light, why is the sky blue? We pose the question to Robert.
It's something that we'll get into later.
Greenberg, professor of physics at the University of Wisconsin in Milwaukee.
What we ought to start with is not why is the sky blue, but why is the sky bright? For instance, if the sun is up there, and you look in that direction and see brightness in the sky, it means there's light coming from that direction to your eye. Now, how does that happen if the sun's over there? And the answer is scattering.
Light waves, like the water waves in this pond, are scattered by obstacles in their path, sending wavelets off into new directions. Air molecules are just large enough to scatter the light coming from the sun, sending it off in all directions. But why is it blue?
The answer is that when you get light scattered off particles, in this case molecules, that are small compared to the wavelength of light waves, you tend to scatter the blue end of the spectrum more than the red end.
White light is made up of light waves containing all the colors of the spectrum. When these light waves hit air molecules in the atmosphere, the blue portion of the spectrum is then scattered or deflected toward the eye.
All right, so blue light is going to get scattered more than any other color. So the question is why? All right, so the larger wavelengths will travel faster through the material, provided that the frequency at the boundary is constant. All right, so why would the frequency at the boundary be constant if that's the case? Any ideas? Why is the frequency at the boundary constant? Only if the frequency at the boundary is constant, larger wavelengths will travel faster through the material. All right, so why would the frequency at the boundary be constant? All right, there's this pause here, a bit of a silence, as if you guys think about it hard enough, you're going to come up with an answer. It's not going to happen. I know it's not going to happen, and there's a good reason for it, because the guy from Harvard was not able to answer this question when I was a graduate student. And he was my PhD advisor at the time in theoretical physics. And it was his first time teaching. And this is an 800 level E&M course. E&M is electromagnetic theory course. You guys are getting the version of it, obviously. So there was a derivation up on the board. He did the derivation. It took him like 2 hours to do the derivation. That was a lot of work. And and he and I didn't get along too well. So from the way he was talking about it, I got the sense that he didn't understand what he was doing. I could see the math, but his explanations were like the book explanations. It was missing a little bit of depth. So at the end of the lecture, I thought to myself, should I or shouldn't I? So my best friend was sitting next to me. It was also a graduate student. So I turned to him. I said, Tom, should I just ask him? Should I ask him why? Because he said the frequency at the boundary is constant, and that's the reason why the larger wavelengths will travel faster. And he said, yeah, just ask him. I said, what if he doesn't know the answer? Because he's my research advisor. This guy could literally kill me. He said, yeah, it's not a big deal. We'll just laugh at him. And I'm thinking, no, that's not the best way to go. He said, no, don't worry about it. Just ask him. I just ask him. He can handle himself. This guy's from Harvard. And so I raised my hand, and this is right at the end of the lecture. I said, you said right at the boundary, you said the frequency is constant, and that's the reason why the larger wavelengths will be able to travel faster. So could you tell us why? Evidently, I was right regarding my intuition. There was something after he was explaining it. I figured that he was covering for something that he didn't understand. And as soon as I asked that question, there was a weird, awkward silence. So he's looking at me. I'm looking back at him. And then he tried to say something, and nothing came out. And so I turned to my friend. I said, I think he's going to give us some mathematical bullshit at this point. And that's exactly what he did. And people started to laugh because they heard what I said. He said, oh, at the boundary, the energy has to be constant, blah, blah, blah. And somehow he was not able to pin it down. Okay, I knew he was not going to be able to pin it down because theoretical physicists, and I spent about 2 years working on theoretical physics, they have a mathematical way of looking at things. All right, they look at equations, this and that, and they kind of lack understanding. Math gets really thick, they can't get to physics under the circumstances. And the explanation for this one is extremely conceptual. All right, this is the sort of stuff that you guys usually have on the test. You get a lot of mind twisters. All right, so why is that frequency at the boundary constant? And I noticed that a lot of you guys try to manipulate the equations and trying to answer your questions, and you guys are not getting full credit for your attempts, because what I'm looking for is a conceptual explanation. All right, guys, what's the frequency? Frequency is number of periods per second, number of wavelengths per second, guys. Here's one single wavelength, 2, 3, and 4. Notice that you got 4 wavefronts approaching, and within the same time period, you got 4 of them actually crossing the boundary. So despite the fact that the wavelength is shorter, because this thing is slowing down, the number of wavefronts approaching and crossing the boundary is the same. All right, let me say it differently. Number of wavelengths incoming and crossing will be the same. Number of wavelengths per second is the same as your frequency. And number of wavelengths per second crossing the boundary is the same as your frequency. So notice that the incoming frequency of the waves and then the outgoing frequency of the waves are the same. All right, so it's the number of wavelengths per second, number of periods per second, number of cycles per second for the incoming waves, as well as the waves crossing the boundary will be the same. All right, you cannot do this sort of stuff. This is not equation manipulation. Conceptual understanding in physics is paramount to your success. For those of you guys who want to get into physics at some point. All right, so once again, this explanation does not work out, so that's something that we will look into at some point. All right, so everything that I just discussed so far. All right, so.
When a light beam, incident at an angle, first encounters a piece.
All right, so imagine this is 1. You got 1, 2, 3, and 4.
Of glass.
Wavefronts approaching.
One side is slowed down before the other.
Crossing at the same time. 1, 2, 3, 4 crossed. 1, 2, 3, 4 approaching at the same time. So the number of wavefronts approaching and crossing within the same time period will be the same, which means the frequencies are going to be the same.
Forcing the wavefront to change direction.
This has been an ongoing debate. So we'll just try to address that question today. Okay, so if you have 2 sunglasses, if you get 90 degrees to each other, you won't be able to see through them. Everything is going to go dark. So the question is why? When you have sunglasses, put 90 degrees to each other, you won't be able to see through them. All right, does anybody have a theory regarding that?
Does the waves travel 90 degrees to each other?
All right, so you're thinking that this may have something to do with the wave nature of light, right? For whatever reason. Okay. Let me ask you guys this question. What's the purpose of sunglasses? Why do we have sunglasses? Is there any particular reason as to why we wear sunglasses?
Like to block the sun so you can see.
All right, so they block the sun so that we could see. All right, well, yeah, that's not bad. All right, so I'm looking for something. Obviously,
the sunglasses block light coming in like from above and below,
yeah,
not from the
absolutely.
sides, right? So if you put 2 of them at different angles like that, they'll block from every direction, right?
And then everything goes dark. All right. Yeah, I mean, the intensity of the light is reduced. That's certainly the case. So it's not going to be as bright. The purpose of sunglasses is to reduce glare. So the question is, what is glare? It's not necessarily the sunlight that's really bothersome, it's the glare. All right. So how do they reduce glare? Right, so that's
30 years ago, space was considered a vacuum, except for a curious clue, the tail of a comet.
All right. So the tail of a comet.
Regardless of the direction it traveled, its tail always pointed away from the sun.
So the tail of a comet always points away from the sun. All right, this got Newton curious regarding the nature of light. The tail of a comet always points away from the sun. So his question was why?
Mystery unexplained, considered a vacuum. Ago, space was considered a vacuum.
All right, so notice that the tail of a comet,
Except for a curious
and regardless of where the comet
clue,
is,
the
it's always pointing away from the
tail of a
sun.
comet.
So which means that something coming from the sun, coming out of the sun, is actually pushing away from the sun. So the question is, what's coming out of the sun that's pushing the tail of a comet away from the sun? Newton thought that this was the proof that the light was composed of particles. All right, only 8 particles through collisions can transfer motion or momentum. Waves can only transfer energy as far as Newton was concerned. Transferring energy means you got this transverse wave coming in, and so you got this, the tail of a comet is obviously made up of dust as well as ice particles. So when the light wave comes in, what's going to happen to the dust or the ice particles? If there's a wave going through it, they can only just go up and down. Disturbance can only go up and down. It's not going to get pushed in the direction of the wave. So if the energy is being transferred, the only thing that happens is it's just going to vibrate up and down. If it's a compression wave, it just vibrates sideways. It doesn't get pushed away. So the only way you can push something away is through particles colliding with other particles. The motion is what gets transferred. So momentum is what gets transferred. So this was the proof, as far as Newton was concerned, that the fact that the tail of a comet was being pushed away from the sun implied that whatever it was coming out of the sun, which is light as far as it was concerned, had to be composed of particles, because particles only through collisions can transfer momentum, which means that only through collisions the particles can push away particles, making up the tail of a comet. All right, so that was Newton's argument regarding the nature of light. And then Newton came up with that argument in response to what Huygens came up with. Huygens is a Dutch physicist. His name is Christian Huygens, who proposed that the light was composed of waves. And the reason why he came up with it is because you see shadows at times around obstacles just like that, which implies that there's some kind of an interference pattern. And if there's an interference pattern, what we know about the interference patterns, they can cause constructive interference as well as the destructive interference patterns. If it's constructive interference, the light is going to become brighter depending upon your light sources, or you can cause a destructive interference, which means that there would be a lack of light, which means that everything is going to look darker, like the way you see shadows. All right, so this debate was settled in 1901 or 1801, 1803, depending upon who you're using as your source, by something called the double slit experiment.
Here's just one of the reasons Young is so clever. He decides to shed a little light on light in 1803. Okay, watch this bit of magic. Here we have a candle, a lens, a card with a pinhole in it, and one with 2 slits. Okay, shine the light from the candle through the lens so you get a nice focused beam. Then carefully place your cards so that the light goes first through the pinhole, then the slits, and voila! Young realizes the light going through the slits and mingling must be coming in light waves, because this interference pattern could only be made by waves. Question is, what do light waves travel in? They decide to call the mystery stuff ether, and the hunt for it shakes up the brains of most of the 19th century's complement of serious propeller heads. Now, the biggest propeller in Germany at the time is a Harumph type, name of Helmholtz, prof at the University of Berlin, and he puts one of his whiz kids, Hertz, onto the case. Here is a very oversimple view, of what Hertz does. Say this water is that mystery ether stuff, right? Hertz is into electricity at the time and wonders if it travels through ether in waves like light, and he finds out it does. An electric spark sends out electric waves moving like light waves, or waves in the sea.
All right, the one that I'm interested in for our discussion, and the rest of it is
made by waving through the slits and mingling.
All right, so this is what you end up getting on the
must be coming in light wave
screen. When you have double slits, this is what Thomas Young came up with. Double slit experiment. Notice that on the screen you end up getting a fringe pattern. You got the bright fringes as well as the dark fringes. All right, so what does it signify regarding the nature of light? Is light composed of waves or particles? What do you guys think? What is it?
Looking like waves so far.
Yeah, so it looks like waves, right? So why did you say waves? Dark fringes obviously caused by the destructive interference pattern, and the bright fringes are caused by the constructive interference pattern. That's it. So constructive interference of light is going to give you, the waves will give you bright fringes, and the destructive interference of light waves will give you dark fringes. That's it. So the argument is settled. Okay, so we don't debate things in science. We look at the data, look at the conclusion. So Huygens 1670 proposed that the light was composed of waves. Newton proposed in 1680, 10 years later, came up with the corpuscular theory, which is known as the particle theory, based upon the tail of a comet. He proposed that the light was composed of particles. So Young's 1803 experiment, double slit experiment, proved that the wave theory holds because you end up getting an interference pattern. Constructive as well as destructive interference patterns will give you dark as well as the bright fringes. All right, guys, whenever you're ready.
C, wave.
All right, so C is the best answer, right? So the 1803 experiment proved decisively the wave nature of light. Give yourself 5 points. Those of you guys who pick C, give yourselves 2. So C is the best explanation.
C.
All right, once again, it's C, right? Interference pattern that we looked at. The interference pattern that we looked at, that's also known as diffraction, something that we will get into later. All right, so C is the best answer, so give yourself 5 points. Those of you guys who picked it, give yourselves 2.